Good to go.
All right, 15 minutes. We'll get about probably a quarter of the way through this in 15 minutes. So this is lecture one. This is the Calibration Validation series of lectures. I think we have this one and then 2 weeks, 1 week. I can't remember when, two more calibration validation lectures. So I'm going to start mostly on the calibration side, but questions for you. What do you think is meant by calibration? And what do you think is meant by validation? I'm going to keep going because I think we're all getting angry, probably a little, at least hungry. Okay, so calibration is the process that ensures that accuracy is maintained in the measurements produced by your equipment. So basically, it is trying to make sure that the measurement you want is made very accurate. So calibration performance of any equipment is compared against a reference standard, some sort of standard. We always have to make a measurement and trying to characterize like a visual response function of your instrument against some standard. In layman's view, that means just converts the raw energy, or converts, maybe that's German, I don't know, but converts raw energy like in volts counts to data and physical units. And calibration assures, again, the accuracy of your measurements. So it is really good to periodically cal because things do drift, electronics drift, optical surface particularly can become fouled. So validation is a documented process that provides assurance that a product, service, or system, in this part, a measurement, consistently provides results within the acceptable criteria. Note that in validation, it's not really a reference standard that we're directly using. We're typically trying to do, I made this measurement, is there a corollary way to get at that same measurement through an independent different measurement technique? Or it could be as like an example of a chlorophyll product from satellite versus a chlorophyll that's derived either through chlorophyll extraction, HPLC techniques, or even a full on. And so validation provides a proof of consistency or consistence across all the methods or processes being used. Okay, so let's see, where are we? Oh, I have 12 minutes. I could probably get through this part. That's what I thought. So let's start with, I'm going to kind of run through different ways to do this. We're going to talk about some, not all, the optical measurements and sensors you've seen. I'm just going to pick 3 to try to talk about how those are actually calibrated. And then we're going to walk through the actual radiometric calibrations. We'll probably only get through that part of it. And then we're going to talk about how do you calibrate actual radiometer that's flying on a spacecraft. And then we're going to talk about a special process called system vicarious calibration. So that's sort of the flow of this talk. So I think you've all seen eco FLBBs or some version of an eco sensor, right? So you know what this is. It's got an emitter and a detector. They're at angles to each other. So you can imagine 2 cones of lights coming out at some angle here on each one. So typically you're doing optical backscattering and a chlorophyll fluorescence measurement. So the first thing you do to try to calibrate your instrument is always have to have a dark signal. So this is sort of your blank, if you think about it. What is my signal response when there's no light coming into the system, going out of the instrument, and then hitting the detector? So the easiest way to do that, take some black electrical tape over the detector, and then you can measure what the dark counts are. That's why they're called dark counts. There's no light actually hitting the photodiode behind it. So for an optical backscatter measurement, I think we've talked about it. It was great that this came after Patrick's talk. The reference standard typically, and most often, or actually for almost all of them, is the nanosphere or the spheres and nanosphere. So what we have here is a sphere that's with very high quality. You can buy these reference standards. You know what the actual diameter is, the particle size distribution around that diameter. It's very, very low. These are all mistraceable. So basically, you're using these spheres then to go into me modeling to figure out what your response function should be. So typically, you do this at 1, 2, maybe different particle size or particle sizes, your standard, and do a concentration versus instrument response function with it. So here's my output and counts. I just basically try to do a dilution of it, or in this case, an addition, drop one, drop in, make a measurement, drop another, drop in, make a measurement. So it's sort of like a concentration versus instrument response. What you need to know there to do this is you have to know the index of refraction of the material. And then you have to do something a little bit more complex, but mostly these are published. There's, again, 2 cones of lights coming out. It's not a perfectly, it's kind of a shape, weird shape where these 2 cones intersect. And so you're actually measuring, you can't see it, scattering, we're measuring over a broader scattering angle. So it's not a perfect collimated beam. These are 2 beams that are intersecting the detector beam and the actual output light beam. So there's a point where those intersect, and then there's a point where they no longer intersect. So you have to know where that is in terms of the scattering angle versus what we calculate as a weighted response function. That's what this is, the response function. How much of the light field am I getting across in scattering angle space? So you need to know those 2 things. Whoops, I went the wrong way. So in chlorophyll, typical way to do this is, again, find some sort of standard. Spinach is a good one. You can buy it online. Verified as possible. And when I was at Seabird, we did a lot of work to do it to a culture, direct to a culture, a diatom culture there, and use that. Again, you roll them up and then you kind of dilute them down and do a dilution series to get concentration versus instrument response, concentration of chlorophyll in this case. Good thing about spinach is it's ready available standard. You can buy it online, but it doesn't look a whole lot like phytoplankton, we think. I mean, it's not the things we're measuring in the ocean, you know. So, but it's also good if you want to try to calibrate your fluorescence measurement to one instant type of species of phytoplankton. We've got the capability to do that by doing this calibration process. I think I'm getting hungry. So we talked about this before in some of the presentations of just kind of driving this back home again. You all did measurements, basically calibration measurements in the ACS before by just putting in that pure water. But the thing I just wanted to hammer down is that the reference standard is pure water. So the calibration file that you have is referenced to that as pure water. So this is very similar to the same standard that's used in benchtop spectrophotometers. Have you ever done that? You put in your cuvette full of pure water, you hit the button, say I want to blank it, zeroes everything out basically. So that's the same thing here. So the important point is when you make measurements in the field with this and you want to actually look at the total absorption, you have to actually add back in water. So I put on the Google Drive there, I put a Excel spreadsheet of just what I think it's at 204 nanometer resolution, a lookup table for the pure water absorption. It's really recommended you calibrate the ACS using pure water pre and post deployment. Some of the older versions of the ACS that use a different white light source were pretty drifty over time. The newer versions are a little less drifty, that uses a white light LED, but also it's really good. So if you're doing it pre and post cal, you get sort of how much my instrument change over each period. Like 5 minutes. You know what? I think I'm going to stop there because I got like 6 slides left that are a little more complex just for radiometric calibration. So. Yeah.
If you have a calibration at the beginning of the event, how do you use both of them?
That's always a great question. It's always a great question because it depends really. I mean, if it's a short cruise, usually you can do a little an interpolation, linear interpolation. But if it's a very large shift, something really went wrong somewhere, maybe window got scratched, you put oil on the window, shifted the response. So it's not the easiest thing to do. Usually, like when we were doing 3-4 week cruises, you know, it's just daily calibrations. So you can actually see if there was a step function. But daily calibrations is a lot of what goes on. There's not a good solid answer to that. More measurements you make, the easier it is to figure out how to make that correction.
I saw that. I saw it out of being. This was great.
Right. Yeah, I have the key for, yeah, the original of that. Thank you so much.
Do you know when the filter goes off? I don't know.
Sit down.
It's good.
All right,
We're on this.
let's get started back again so you can get into thinking about polarized light in the lab. So, so far we just covered some really basic IOP measurement calibration processes, skimming over the top of this. Here, we're going to move into the calibration of the radiometers you did in the lab. Most of those radiometers, the process of that. And then we'll go over another process called satellite calibration method, and then the system vicarious calibration. So in terms of this, what I'm about to say is a generalization because it's not quite true, but the method for the absolute calibration of radiometers, the standard and there's a standard, which in this case for irradiance and radiance, it's a very traceable light source called an FEL. It's a 1,000 watt output FEL lamp, and it also has to be exceedingly stable in its output. So here's a little tungsten coil, comes up through it. It's very bright emitter tungsten is of light when you put in enough wattage to that lamp. So one huge requirement in this process when you light this lamp up, you have to have like massive accuracy in the amount of current you're providing and the amount of volts you're providing. It can't vary by less than, I think, a milliwatt. So it has to be very stable because otherwise, if it's not, you get different voltages come in. You start to get this vibration a little bit more up and down on that tungsten, and that just creates all this noise in your light output. So when I say that's typically what we do here, so we buy manufacturers, radiometers from companies, they typically use this method. Now the actual, how do you get at the absolute measurement of radiance irradiance? It goes all the way back to a cryogenic system because you're basically measuring again the emission output, measuring that thermal output energy. That's how you get to actual pure calibration. So this is what's called a transfer function. So There are different ways that NIST has, the National Institute of Standards and Technology has to do the cryogenic calibration that really sets the standards for the measurement itself. But this is a transfer function. So this is what the light output looks like, wavelength versus irradiance coming out of that lamp. And that doesn't look very much like what we saw on the dock, right? Kind of the actual opposite. It's a very, very red rich light source. Really, really poor in the UV blue. Not a whole lot of output, and as you can imagine, the uncertainty is all weighted that way too. It's a lot more uncertainty in doing the calibration process because your light output's not that high. But it's a really stable way to do this. It's a really, really stable way to do a measurement or calibration.
So the uncertainty is higher where the lamp's emission is lower,
Correct.
but then on the right side where it starts to emit slightly less in the near infrared, the uncertainty still doesn't kind of go back up again a little bit.
It kind of does. You're sort of getting in to a couple of different things. Starting to get into getting close to the infrared there. So there's some other effects in terms of atmosphere control room effects you have to really control for in terms of doing this measurement correctly. And so it does go down slightly, but it's pretty small and it's oftentimes around the level of all the other environmental things come into play there. Okay, so yeah, go ahead.
By the lamp, like, is this something we would see in a leaflet of like a handheld?
No. Yeah, this is the only place you'd really ever see this is when I'm about to show you in a radiometric calibration. Because this is basically there's like constraints. These things can only be turned on for 40 hours before they go out of spec. Meaning you can't use it for calibration anymore. They're highly sensitive, even more so than the ACS. Don't put your thumb on an ACS window. And you touch one of these, you have to throw the whole thing away.
So 40 hours?
40 hours of burn time, yeah. So that's, and again, this is all, we're gonna get to this. You're trying to really reduce all the uncertainty and measure, get accurate as calibration as you can. So if I put my thumbprint on here, and all of a sudden the radial output changes massively, you've got grease on it. So all that adds into it. Now your spectrum is gonna have wiggles on it.
Just a good idea of how much, I guess, right, why your calibrations for your instruments are so expensive. How much is one of those lamps that you only get like 40 hours on?
They're usually about $2,000.
With calibration for the.
Yeah. And you get 40 hours from it, so.
But how long does 40 hours last you? Because I imagine you wouldn't.
Well, yeah. Basically, it takes about an hour, 70 minutes to do a count. Now, we don't turn the instrument on for all that, or we don't use all that 70 minutes to actually make a calibration. But again, you're trying to make this light output as stable as possible. So you have to warm it up for 20 to 30 minutes and get it into a burn state where every little molecule of tungsten's emitting exactly the same amount. So you have 30-minute warm up, setup time, calibration only takes 15 minutes. And then you have to burn it down slowly, ramp down the amperage to bring it back to a stable state before you can actually turn it on. That takes another 30 to 40 minutes.
Are you getting like doing cereals? Like
Yes. That's the classical way to do that because the actual turn on time when you're making a measurement can be as short as 5 to 10 minutes. So yes, it's kind of a batch run. Warm up the lamp, run as many as you got in front of you, and then turn it down or turn it off again.
And then after, when you get to around that 40 hours, does the output start
It's
looking
drifting.
weird?
No, it did. It's still pretty stable in its spectral output. It just it starts drifting down this hole. It starts getting dimmer and dimmer and dimmer. But it's a very slow. I mean, you can use these up to 200 hours. So what we usually use these is not in an absolute calibration, but if we're doing other characterizations, it's still a good light source for that. But
Does anyone do the calibration themselves, or do they always send it back to the manufacturer?
There are not a whole lot of, I mean, the instrument manufacturers do this kind of calibration if they're making a radiometer, mostly in the ocean. But there's not a whole lot of facilities in the world that do this calibration, and this guy and I are setting up one at Oregon State University right now. We're that close. And there's another one in Estonia. So there's like 3 or 4 really. There's one in Hawaii. So there's not a whole lot of them around the globe. NIST does them. Most of the National Physics Laboratory, the NIST equivalent in England, they do them too. Okay, so we're going to go over the calibration process for irradiance. So here, sort of looking down on this setup, you have an alignment laser and set at some distance. Here's your FEL lamp. Now what you have is these shields, we call them kind of baffles. So basically, I'll get to the point of that, but they're adjustable baffles. What you're trying to do is create a little cone of light that doesn't massively overfill your sensor, but just fills enough of your sensor. And so then that is mounted, and you want to make sure they're all on the same relative plane this axis and the up and down vertical axis as well as making sure this is directly in alignment with the lamp. So take the alignment laser, we shine it kind of right next to the center of the filament, make sure it's all aligned well. There's a translation stage you can add in here. So if I add, this is again, what type of a radiant sensor? What's the key characteristic of a radiant sensor to recognize it? You got a radiance and then a radiance in your hand. How would they look different? Cosine collector. So what happens if I rotate the instrument this way? What am I measuring?
Cosine response?
Correct. So that's why this is here. Because all I have to do now is start rotating that at different stages, and now I'm measuring the cosine response of the instrument. So this is a setup of the room. They're really cool rooms to be in because they're literally zero photon. Without that lamp being on, it's a zero photon atmosphere. So I demonstrated this to Alexander once we got all the rooms set up and painted. Black walls are special. It's highly expensive paint. To paint this room, it cost me $6,000 just from the material for the paint. So these are the highest absorbing paint you can buy on the planet. Because we're trying to do is calibrate the only light source we want in this room is from that lamp. So if you go into my room that I've set up, turn off the lights, shut the door, turn off the lights, you cannot literally see, even at a short distance, your hand. It is totally dark, zero photons. And again, the reason for that is we only want to measure one light source. And so these shields also not only are just baffle systems where I can open up the aperture, but there's curtain systems here that block one side of the room from the other. Why would we want to do that? We're trying to measure all this light, right? It's coming from a lot of angles. So one question would be, why do you even need these? Well, because even in that zero photon atmosphere, you got other stuff a little bit in the room. And so what you're trying to do is not measure any what's called stray light in that room. The light that's bouncing off walls, people, all that kind of stuff. And that's why this room is set up into, nobody's allowed over here while we're doing a measurement. People are allowed over here, and then there's going to be another place where people sit behind a curtain as well. So it's a complicated process. These are some pictures of that. Here's sort of that aperture shield that opens up. There's another one, the radiant sensor, the 7-channel radiant sensor. So we also learned when I went over this, what does the radiance do with distance away from your point source? How does it, what's that?
Density increases.
By what factor? 1 over the square of the distance between your lamp and whatever target you're measuring. So those FEL lamps that we buy, they're all calibrated at some set distance. In this case, it's usually 50 centimeters. Now, depending on what type of sensor you are, you may need to sort of move the slant distance away back and forth to kind of bring it in range, so you're not always measuring saturation of the sensor where there's not enough light. So this distance can change and it's variable. Sort of correct for that distance. There's a factor in here. Where is it? It is the distance from the FEL to the sensor. D0 is what that distance is from the manufacturer, centimeters. And then the D is the actual measurement in my lab, or the distances I have set up in my lab, and there's the square foot. The manufacturer provides us this measurement, the actual irradiance they measure in the lab and the calibrated too. So then it's just taking the signal output, actual measurement value minus the dark counts of the instrument, the noise floor of the instrument. And that derives the actual calibration coefficient that's used to calculate. Yeah, I'm sorry, he would.
Why do we have confidence that the lambda radiant, why do we have confidence in the lambda radiance value?
Again, because it's mistraceable. What that means is that there is a chain of custody. So we do this cryogenic calibration that's done against a black body radiation environment. That's why it's cryogenic. Then you get another transfer and say, okay, now I've got this one response. Now, if I use a different light source response, how does that measure? So every step of the way, you're doing this transfer. That's what I call why mistraceable. It all goes back to the physics of being what a black body radiator transmitter does. So it's all based on the third of the relationship, 1 over the T to the 4th temperature, or T to the 4th temperature dependence on the actual emission of property over a light source. So this is just transfer. FEL is another transfer way to do that transfer. So basically I've got one property I've measured. Now I want to go out and say, okay, you know what the light spectrum should be. Is this lamp source measuring it? So it's the same sort of thing for lamp detector measuring it. Yep.
So kind of a two-part question. So you get 0.4% error at 1 millimeter of distance change, which is like, that's kind of crazy.
Very crazy.
So like, I guess the first part is your rig just automatically set up at 50 centimeters so that you don't have to.
No, I have
Yeah, you
to
got
change
to-
it. I have to change it because it depends again. Some manufacturers of irradiance have one dynamic range and some have another dynamic range. So at 50 centimeters, it may be too bright. It's way up at kind of the top end of the scale. So I have to pull that back or not. So I have to move that distance. But what's not shown in here is all this optic stuff and the holders and clamps are all on a very highly gated measurement scale. Gives me 1 millimeter
And then like, so
ratings.
cosine collector, it's like protruded, right? So is that to the?
That's to the,
very
that's,
front face, and then
yes.
for like the emission, is it just to that, like the glass phase?
For here, we'll get to radiance, but for irradiance, yeah, it goes right up against the cosine collector, the distance from the cosine collector to the center of the filament.
Yeah.
So it's pretty trick because you got pretty bomb system here. So when you put the FEL on a fixture to light it up, there's known distances and you have to get out calipers, so we can recalibrate them. So it's a meticulous process. Okay, so I had a good question for another thought question. So I talked about that. These are curtains, right? So when we were out on the dock at the PISAS system, what am I measuring if I close this off? About what we did there, kind of? Straight light. Straight light, yeah, that's how we kind of got that skylight value, where we blocked the light. We blocked the sun. That's a good way to check if there's really any light in that room. Just close all this up, close the shutter system and say, it should be pretty flat. It should be very flat. But if I can see any spectral light coming through, that means I got to seal the room up better. Okay, radiance. Here's my lamp, my baffle systems. Here's what's either called a plaque, tile, target, So back on the dock again. We had that big 99% reflector plaque. Does this look familiar? Kind of the same setup, right? So, but what would I expect to be coming off of here? Should be seeing the spectrum from the lamp, right? So it's the same kind of thing. You put your radiometer now at an angle 45 degrees to this big giant plaque that's mounted here. You set another distance here because this is again just a radiance transmission. This is a radiance propagating. That's a it's a light source that emits in all directions. But then this doesn't get really changed with distance. That's the principal invariance that I talked about. But you have to make sure that your illumination making sure these shutters are open wide enough to fill the plaque. Because now, like we did with the water, you've got a field of view that's staring at that plaque and you don't want it to clip or be too big. So go ahead.
How is the plaque calibrated?
I don't 100% know. We get plaques from companies that I think most of it is based on material science properties. I think there's a check with it. Basically, what they know what the material is, then, and then if they have a smoothness of it, they know what should be the reflectance property off of that. I'd have to check on that. It's a great question, Evan. But what we used out in the fields, I tell you, it's not Spectron, which is what this material is. It's just basically white plastic, which is still pretty good, as you saw. It has good reflectance. It acts like a Lambertian reflector. This material, Spectron, is just as bad, if not worse, than the FEL in terms of you can get it stained, you can get it aged, you can get it, and you cannot try to mount this thing. It's really difficult to mount this thing fixture without touching that white. Because again, if you touch it, now you've changed the entire reflectance properties off it. It's probably no longer a Lambertian reflector anymore, which is what's required to do this. You take your instrument, you bump it by accident against it, and it's got a dent into it. Send it back to the company, and what they do is resurface it. They basically take off enough thickness on that material so that dent is gone. This thing can cost up to $15,000. So expensive. So, all right, it's pretty much the same thing here again. Here's the light lamp output. We still gotta, make sure we're reducing the lamp output as a function of distance. Here's the spectral reflectance properties of that spectral plaque. So hopefully this is like a 99%. It's pretty close. This is more like a 99.8% reflecting material. But I normalize that by pi, and then there's some other things here. A correction factor, because this plaque really isn't a Lambertian reflector. I've got, maybe really good Lambertian here, but out here it's not very good. So you may have to map out the actual how well the degree of quality this plaque is for the Lambertian. Luckily, the manufacturer gives us an error function sheet for that. I don't typically use it because it's astronomically small. And then there's the same essentially measurement. Signal output when it's illuminated minus the dark count. So pretty cool that we did that on the TSRB, or sorry, in the PISAS, because pretty much made these same type of measurements. All right. For radiance, there's another way to do it. Remember what I talked about for the little golf ball, or I kept calling it a ping pong ball style PAR sensor, right? So I kept mentioning that it's kind of like an integrating sphere. Get your detector coming inside of that little bottom of the ping pong ball. The idea there is it's white again. So what does white do? Especially if it's made out of spectralon, the coating inside of the sphere is made out of spectralon. It's just bouncing light all over the place. So it should be as I pump and put one of these FEL lamps on one of the side of it into a port. This is a port. Here's the output port from this. An integrated sphere illuminated by an FEL. So the light is pretty much now Lambertian style light that's coming out. It's going equally in every direction. So these are really great to use. They have some other different constraints and cons to them. One, it gets hot in that sphere really quick. You can put up 100 to 1,000 watts into that sphere, and man, you're cooking inside of there. So you have to really gate. And we've got like a system that has blowers on it to try to keep the sphere from heating up too much. But the big one is, let me go back up. So the measurement of the radiance coming out on this port is measured by, or is as a function of how we do this, is the input flux on the numerator, the air surface area of the inside of that sphere, times pi, obviously, and then we have to do a multiplication adjustment factor, where basically the inside of the sphere is not contiguous. We've got holes in it where there's no spectron. So we have to account for those holes because that could change, you know, how Lambertian and how equal it is actually inside of that sphere the light is. And that's important where most of that air comes in is because you don't insert your instrument into the inside of slide it through the opening, and put it at some small distance away. So typically for radiant sensors, remember those, they have a glass front on them. What does glass do pretty well? If you're coming at angles, it reflects pretty well. So part of the problem is if you may be coming in here, going through the air glass interface or just bouncing light right back into the sensor. So if it's seeing anything on the side of the sensor on those Gershon tubes and colors, it could be changing the light a little bit and then going back into the integrating sphere. So that's what this correction factor says too. Okay. I'm geeking out because I love this stuff.
What's the color of the pool?
Pardon?
What's the color of the sphere?
Inside of it, it's purely white. It looks like that material I showed you in the plaque. It's the same material spectral on it. So it's like one of the whitest materials you can find. On the outside, it's aluminum coating that's got different thermal coatings on top of it to try to help radiate some of that energy and heat out. I'll show you one here in a minute. All right. So we just talked about a handful of uncertainties that in both processes. Here's a list of them that comes as sources of uncertainty in doing both the radiance and irradiance measurement. There's inadequate mechanical setup to actually have it aligned right. Was it an unseasoned or a seasoned lamp? Is it getting too old? Did I put a thumbprint on it accidentally? You take all these things into account. And this is even like NIST is about this low. That's the best you can do. Mean square in terms of total uncertainty, about 2%. Really, really hard to drive it down. And I would be very cautious if you see somebody reporting, oh, I did a cal, and I have less than 1% error. It's really hard. I mean, meteorological agencies can't even get that close using this type of similar method. I'm pointing this all out for the later stuff that's going to come up on SVC. Sorry, you had a question?
And maybe you mentioned this, but in your calibration room you're setting up, do you like filter the air for dust?
Yep.
Okay.
It's humidity controlled because we want to have this constant moisture environment. It's got to be pretty low, not too low. We don't want to get it so cold or so dry in that air that now we're going to get static, which is not great either on surfaces, just as dust collectors. And then you have an air filtration system as well. So yeah, there's a lot that goes into this. Okay, so just remember that it's 2%. If you're doing this, if you do a cal and your uncertainty is 2%, you're doing awesome. All right, so now we built this giant OCI satellite. Big system, it's not like the detector or the system, the sensor is as small as what we have in the field, it's pretty big. But here's integrated here. And for context, you can't really see it, that integrating sphere is about that tall on them. It's a huge one. And that's because you need to open this aperture enough to be able to actually fit the rotating optics in the plane of view of that output here, because it's much bigger optics than what you're. So that's that. So sensor satellite sensor calibrations, we're going to talk about this. What is that meant by this? We're trying to really do the calibration at the top of the Earth's atmosphere. That's what we're trying to derive, because that's what the satellite's measuring all the light coming out of the Earth at it. So there's really three types of calibration characterizations for ocean color sensors that are needed. One is what's called a pre-launch calibration process. We just kind of went over this. It's just on a grander scale, bigger scale. It's the same kind of radiance calibration method I showed you. In this case, they use the sphere method. There's another way to do this, which is a really bummer, but it's really complicated optics. You can use a variable tunable laser as your light source and just scan through all these different wavelengths and pump it into a very trick optical arrangement. So you can start looking at different things also, like actual out of band response. But then you launch the satellite, goes up into the orbit of the Earth's atmosphere. And now, you know, if you ever watched a rocket launch, you should run this nice one on a pace online. It's a pretty violent event. You got a lot of vibrations. You got the satellite sensor in the nose cone. It's rattling around there. You get it up. The boosters are popping off. You get it up in there. Nose cone opens and then it pushes it out. How does it push it out? Exploding bolts. And then they start moving it around to get it in attitude and orbit and height. And how do they move things in a vacuum? Well, they typically use gas canisters that pump out, you know, and push things left and right. Okay, it's a vacuum, right? And now we're putting gases into a vacuum. So any attraction to surfaces on that satellite rapidly suck up those things, those molecules. So that's part of it. So after we launch, we have to recalibrate it again somehow, because it's never going to be the same as when we calibrate it on land. So there's a couple different ways to do this. I'm not going to go over the details, but an OCI, for example, twice per day, rotator looks at the moon, the surface of the moon, twice per month. Sorry, not twice per day, twice per month. It looks at the surface of the moon. So why would it want to look at the surface of the moon? It's semi-decent plaque. Problem is, it's not very Lambertian. You can see that from your eye. It's got dips and valleys and all kinds of dark spots, bright spots. But at least it gives a way to kind of say, well, moon's not really changing that much. I just know the orbital characteristics. I can kind of really estimate. Yeah.
For calibrating the moon, since it's so spotty, is it like just an average value of the whole surface, or is it like?
Yeah, I think you'd have to ask Jeremy about this. I know they're setting up the lab, but yeah, I think it is. It's just kind of staring at more of a spot in the moon. So
Yeah.
the other way that, and they do it only twice. They only do it twice per month because they do it the day before and the day after the full moon. So they're not looking at crescent moons or anything. They're trying to get where the albedo is the greatest off the moon and consistent. The other way is they have a solar diffuser, two sets of solar diffusers. So now they rotate it and look at the sun. Well, that sun's pretty darn bright. So it can saturate the sensors in a heartbeat. So they have these diffusers, basically similar to like a cosine collector, sort of like a neutral density filter. We're just knocking down the amplitude of the light so we don't make it screen enough, make all the electronics get scrambled. So that's usually done You know, at the start of the mission, they do it more frequently, probably daily or so. As time goes on, they use it less. The biggest problem with a solar diffuser is, you know, now you're hitting the diffuser with the black body radiation that's coming off the sun, which is tough to make materials in a diffuser. They don't age over time quickly. Okay, and then there's a process. It's on orbit. We've done the best as we could to try to keep it and correct for the calibration errors from the launch. But that's all top of the atmosphere. It's all relative to the top of the atmosphere, or zero atmosphere method, moon and sun. The measurement we really want is the light coming out of the ocean. So this is a process called system vicarious calibration, and it's used in situ methodologies. So what is system vicarious calibration? It's calibration with sensors in space. It's helped to fine tune the calibration and particularly keep it more in check with time that is relative to a observation in terms of scale of the light coming out of the ocean, many parts of the ocean. It's specific, and this is why it's called system, and I'll show you the graph in a minute. It is specific and dependent on the quality of the atmospheric correction that's done. So it's a system calibration. Because again, think of it more of I'm trying to make sure my top of the atmosphere irradiance measured is correct. So it has errors in calibration due to the atmospheric correction errors. The data has to be the highest quality because what you guys looked at too is that the radiance, even in the sky irradiance model, is much higher than the water leaving radiance, right? So if you're really trying to get at a good water leaving radiance, your errors have to be really, really small. So the overall process of system vicarious calibration, and this thing is twitchy, or maybe it's just me, is SVC is defined as the set of gain factors that when applied to the observed top of the atmosphere radiance forces the combined instrument response and the atmospheric process to reproduce the expected water leaving radiance. Again, that light's up here. This is the light we want. So again, satellites up here. Here's my hypernav. Here's this atmosphere. This is our target. This is what we're trying to match. The water leaving radiance in the ocean at some space and time. There's my target water leaving radiance. Here's the atmosphere contribution to that total component. Now we've got water leaving radiance. We've got the reflectance of the atmosphere. We've got Rayleigh. We've got aerosol. Radiance coming off, scattering and things. And so the gains are basically my target value I measure in the ocean through a propagation to get it through the atmosphere over the actual top of the atmosphere satellite measurement. So again, I've got to take my LWs that are measured in the ocean, propagate them through the atmosphere back in the direction the satellites. That's the purpose. That's what we're doing. But you need really high twitch, high quality measurements in radiance, upwelled radiance in the ocean. There's also another challenge that comes with this hyperspectral. We've talked about this a bunch of times this week. Here's the old heritage multi-band kind of spectral outputs, like multi-band. Here's more continuous spectrum of pace. And I wanted to show you this because I keep getting pictures. So here is essentially a plaque measurement that we did like outside. Took our radiance measurements, used plaque, then we got out of that what the actual ES or radiance value should be. And this was from Mount Mauna Loa Observatory. We went up to the top of the mountain observatory to try to get out of the lower atmosphere as much as we could. And so that's what these are. Here's wavelength, the radiance, and again, sorry, I skipped over that. So OCI is at 5 nanometer resolution. It measures at 2.5 nanometer steps. Really, to do a good calibration on this, you want to at least, get sort of a 4-to-1, 5-to-1 more improvement in spectral sampling. So, and why do you need that? Dang. Why do you need that? It's because there are all these sun atmospheric absorption bands in there. So once you start getting down to like 2 to 3 to 4 to 5 nanometers, now little band functions going over these things on the top of these things, so you can start to see them. But at 5 nanometers, you're sort of averaging over some of those little tiny points and getting the higher sides, the real actual sides, the water leading for the sky rate or the total ratings coming through the atmosphere. So you really need very high resolution, but you also need then to make sure you're accounting for all these absorption valleys in your spectrum. So this is the one we kept coming back to, it's about 659. You see it's one of the biggest peaks, and there's a couple of oxygen actual peaks in here. Some of these are more of the solar band things like iron and calcium. It's pretty much, what a lot of the sun components are made of. So, all right. Yeah,
This is from the hypernav, right?
this is from the HyperNav.
Yeah, so the hypernav, right, Andrew's kind of machine, think about the HyperPro and the PySAS and even the HSRD, right? You guys got that sun spectrum. And then look at this, like, I guess, can you guys see the difference in spectral resolution? But you have much more detail with this new system, which is super helpful for base level.
Yeah. I'll get to more of a description of the HyperNav, but spoiler alert, the HyperNav measures at 0.4 nanometer spacing.
Is the
Yep. Oh.
HB beta, is that just like where?
Yeah. Yeah. The singlet hydrogen. Okay. So if we make enough of these in situ measurements and their water leaving radiance, they have a whole bunch of constraints on how to do this and what's acceptable for a qualified water leaving radiance is appropriate for SVC. But historically, they've been doing this SVC process since the launch or pre-launch of CWIFs. So this has been the actual adjustment factor that they've used for most ocean color satellites across the globe. There's a study looking at CWIFs and aqua. So what this is 3 different wavelengths. Here's the gains that I told you. It's the in situ measurement of water leaving radiance that's been propagated through the atmosphere over the actual top of the atmosphere. So all these are just adjustment factors. But what they learned is it takes about 40 before you start to actually get to a solid mean of what that adjustment factor looks like, 40 to 60. And that all these were made by station at Moby, which I'm going to explain in a minute. But Moby does about 15 to 20 measurements that get only qualified for SEC, even though they're measuring daily. Only about 15 to 20 of those actually get accepted for this process. So historically, it's taken us 2 to 3 years. That's how long it took to collect the data. Say, hey, we got this nailed now. Now it's well calibrated. It's a long time to wait for data that you're trying to derive POC from an algorithm relationship that's based on IOPs that has to then be transferred back to an AOP measurement. Your uncertainties are just adding all the way up. So as I said, where you need to do these measurements and how you need to do these measurements is highly restricted. You want to go into places where there is no atmospheric aerosols. There's no aerosols. People want it to be as like Rayleigh as possible because it's more predictable. Hard to find those places around the globe, but not impossible, so that's not bad. Sea surface should be free of whitecaps and have no wind. It should be a lake out there. You don't get all those speckle effects as part of your in situ measurement. Water leaving gradient should be over spatial scales larger than the pixel resolution. Usually it's like a 5 by 5 kilometer box centered when your measurements centered around your measurement. So the radiance has to be completely the same across that. Can't have any clouds, obviously. Can't have any variability in the optical properties. And oh, by the way, you got to have less than I think it's 0.5 micrograms per liter chlorophyll in the water. And there's other specs that other people have published on backscattering as well. So very restricted. They have to be totally homogeneous over the penetration depth. And they have to be really low. So what are we trying to do like we did in the atmosphere? We said we want Rayleigh. We want Rayleigh bands kind of conditions in the ocean. Also, you have to make these measurements within plus or minus 1 hour of when the satellite is covering your point. And as I think Kelsey showed, there's a lot of ocean color radiometers or satellites rotating around the Earth. So the satellite overpass from all these satellites come over at different times of day. So yeah, it's not easy to say, I'm gonna just measure once and. But we talked about this too last week or earlier in the week. I showed you this picture of Moby. Here's the one that was in the Med Sea. Both of these systems that we talked about, this is sort of the fixed mooring kind of setup I showed you. Here's the 3 different arms on Moby that have the radiometers, LWs and EDs on the arms. Sol was set up sort of the same way. Another mooring based one. I'm not going to cover the Sol too much because it's not as frequently used and maintained as much now. But here's the Moby setup. We've got first the mooring that holds this whole system in space. So this is off Lanai, the east of Lanai. So it's about a 1,200 meter water depth out there. So you've just got to have this whole thing to just keep you in place in the mooring. Then it's got another mooring that goes out and holds this measurement mooring. It's sort of like it's not a mooring, it's more of a tether buoy system. And that's what this is. To get 3 meter buoy or 3 meter arm where the radiance and irradiance sensors are out at the end of these arms. Cool thing about Moby is they're not real sensors out at the end of the arm. They just are what's called the 4 optics. So it's a light collector, it's your Gershon tube, and it's probably, folding optics, but what happens is then they run fiber optics down to each of these through the center of these, let them up to the actual 4 optics. And all the spectrometers and everything are actually here. So it's a pretty complex design, trying to run fiber optics 10 meters down through a little tiny pipe. Yeah.
Some questions. Why is it so far? I'm seeing that it's 12 miles off the coast of Lanai. Why did they pick out so far? Is it to avoid?
That's the other one I didn't talk about. Yeah, I only kind of is a much more expanded list, but you don't want to get you want to be like 10 to 20 miles or 20 kilometers offshore, so you don't get sun glint or not sun glint. You don't get land effects adjacently, land adjacency effects. Cool. It's pretty blue out there. The pretty constant conditions. I think 5 years ago, they relocated a little bit more to the south. They just found out that it was a little bit too much north to Lanai. It was catching a lot of the trade winds that would come around the island. And it just would fill up a lot with whitecaps by the time the satellite came over. All right, the Moby system, like I said, has been around for a long time now. It has been very extensively characterized. They do stray light, much stray lights bouncing around inside of the system. Done a lot of pre-post calibrations of the system. Moby was on this routine of every 6 months. That whole attachment tethered part would get pulled out and the brand new one would be put in. But during monthly, they would go out, put divers in the water and tiny cleaners, clean the windows and the faces. So it has a really long history. They've done a lot of measurements around it using different other radiometers like hyperpros and things to try to really characterize it. One have been a very highly characterized site. So recently, the Moby team just created another version called Marownet. And so that was a pretty big giant setup that mooring was, and even the part that actually had all the radiometers. You can see it. So what they did here is they tried to miniaturize that a little bit and make it more transportable. Because, you know, if you laid out that buoy, that whole marker system, you know, you got 45, 60 feet of system there, and it was really took big ships to turn this thing around. So they made a smaller version, made some new enhancements to be able to measure all three depths simultaneously at once. Beforehand, they had to go 9 meter, 3 meter, 1 meter depth. So these are some pictures. So this is the surface buoy part that's holding it to the anchor. Now the arm part of it. David Antoine in Australia working with it, and Ken Boss's team. So the other system, which we came up with, and Niels is not here, but Niels, Robert Fruin, Marlon Lewis, Emmanuel Boss said this, you know, Moby's really cool. We loved it. We did a lot of work around it, but man, that seems really expensive. So we came up with the context of this is why not put the radiometers on profiling floats, Argo type floats. So this started a long time ago. Niels and Manuel and others started placing little tiny radiometers on Argo floats and trying to demonstrate that they could last long enough in the ocean. Did a great job with that study. So we said, okay, great. We'll take an Argo float. We'll attach a new radiometric system that meets all the requirements to do the calibration, in situ calibration for PACE. So we had to create a whole new 4-optic system, created new spectrometers that had very high spectral resolution. That's what's all in this center container. And just like Moby, we use fiber optics to connect our light sensor. Here's our radiant sensor, fiber optics that go back in here. So why do we have these arms? Does Moby have these arms? Make a guess.
Shadow gauge measurements.
Correct. If the sun's here, it's casting a shadow, and now my part of my portion of light is in the shadow. That's why we have two, because we're always guaranteed one of them is not going to be in shadow. The other purpose is it's redundancy. What happens if one of these really gets banged, goes out of cal? Now I've got two redundant sensors, which is also a nice thing because it gives me a way to do like a relative measurement of uncertainty. How far off are both heads? At least in the measuring. So the other cool thing here is we can bring this float right, you know, up to the surface and have it hold there. So we pop our head out, here's our irradiance measurement, get the antenna going, we transmit our data off through iridium, away we go. Here's the air sea surface. And if it was like a lake out there, this is 10 centimeters below the surface of the ocean. Why would you want to do that? Because as we saw with Moby when we talked about this, I got 6 meters, 9 meters, 3 meters, 1 meters. I still have to use K to get it to just below the sea surface. It can be wavy there, it can be all kinds of stuff, so you can have a lot of air. If you're slightly off in K, like I said, your L0 minus could have a pretty big error, depending on the quality of your K you're making, because it's got to be propagated to the air sea surface. So we decided why not have that measurement be just like right below the sea surface as close as we can. Let's see. So our spectral resolution is 2.2 nanometers. Like I said, our channel spacing is 0.4 nanometers. We actually go lower than this, but I can't calibrate the sensor using an FEL because you saw that the FEL lamp output and the UV is crap. So I go down to 750 or 780. That's the usable range, but the actual spectrometer is making it from 200 nanometers down to about 1,000 1050 nanometers. So that all results in one measurement, 2048 points. I got two of these. And I'm measuring a little over a hertz. So park at a depth, go park overnight, high my ascent rate such that it pops out, starts connecting. Right as the satellite's going over, I make a 3 to 5 minute measurement, collect data there. I spend an hour and a half sitting at the surface trying to pump that data through Iridium. So that's my number one power consumption is Iridium. Try to get all that offload of 150 lines of data from each head. Takes a long time. So why did we want to go to a float? Some really good advantages of doing that. You get more of a good profile, so you can do more estimates of K, different depths. You're reducing errors in the extrapolation. If you go park down deep, that's what they showed in the first kind of putting optics on Argo floats. If you park down really deep, it really reduces the fouling rate. So we park ours somewhere between typically 500 meters and 1,000 meters depth. And more importantly, they're portable, easy to use, and less expensive than a whole Moby system.
You may have said this, but how do you power this?
There's batteries in here.
Okay, and how long do you think each of these sensors can last?
Right now, because of mostly again, Iridium transmission costs, we keep these out about 60 days before we run out of battery. Obviously, these are each, so we turn them around about every 60 days.
Okay.
Yeah.
The sensor at the top is the downwelling radiance.
4 channels, 4 discrete channels.
That's the cosine collector.
Yeah.
If I remember correctly from your presentation from a couple of days ago, I thought that was the one where it's either designed to be in air measurements or in water.
It is in air, and we're regretting using those because it gets, there's a little well. I showed you that in the cutout, and then this salt water just kind of rolls back and forth all over it all the time, and so can't. So we need to go and put it back in water.
Is that a wiper that's on top?
No, this is the Iridium antenna. This is the CTD stock, and that is our 4-channel OCR. We also have on board so this is the HyperNav, the thing that we lovingly call the copepod. So this little egg sack and it's antenna. So what was I going with that? So there's batteries on board, but even with the CTD, it's not high resolution enough. We're sitting there, and so problem is we're trying to propagate over this 10 centimeters, but there are waves, so they're kind of, in the mean it's 10 centimeters, but the heads are kind of dipping underneath. But they're not real deep, it's like a quarter meter, they're just bouncing force. So that tiny distance, you have to have really super good accuracy in your depth measurement. Otherwise your Ks are going to be blown out of the water, literally. So we have a very high resolution pressure sensor on this system as well to be able to get the accuracy we need to pretty accurate Ks. Yeah.
Do these just go up and down, or do they move over?
Good point.
These?
These go up and down, but they're drifters. They're ocean drifters, like an Argo float is. I have no way to control this, was part of the problem. One of the things NASA always wanted too is just, I don't want to collect measurements all over the globe and have it go crazy. They want to have enough consistency at one spot, like they did with Moby, that you kind of can, what's going on there over a seasonal cycle. So that was the thing we had to deal with in this system. So this is our program sort of sketch we use. So first of all, in order to do this correct, we have to have best measurement quality we can in the LW. So it has to be traceable, it has to have very less than 4% uncertainty in the total measurement. We have to have QA, QC. These are all things when NASA put out with the proposal for this. They had to have data and delivery in real time. They were saying, you know, real time is like less than 24 hours. We'll get to this. It takes us, once we acquire the data, usually it's processed in about 90 minutes and on the web. We had to add this process called a site selection process into it. I'm not going to go over too much of that, but essentially, remember all those SVC criteria? Yeah, we had to go through and do this, take historical ocean color data, other data, and try to find spots in the ocean where it's really low chlorophyll, really low winds. So we have this whole process when we think about, we're going to go here. We go to the historical, seasonal kind of views we get from satellites and say, do they meet the actual criteria there? Same thing in the, we use atmospheric models, we use historical aerosol models to say, is the atmosphere clear enough there most of the time? But, so how many of you have done hot air ballooning? Anybody done hot air ballooning? Gone on a hot air balloon? How does a hot air balloon not just go wildly off and they have to go, you know, it's up, going up vertically? You're taking guess out in it.
Entire cells move in different directions.
Correct. They use shear, basically, air currents going in different directions to try to steer it. So that's what they do. They turn off, they let out air in your balloon to lower it. They put in more hot air to raise it. So they're finding these little currents, and they're trying to just hunt and peck to say, I got customers, what I really want to do is just kind of go in this circle and bring them right back to where I launched the balloon. Works great, you know, for hot air balloonists, unless it's blowing like snot. And it's only one direction in the atmosphere, the winds. So we said, why not use these drifting floats and do the same thing? Find these areas in the ocean where there is shear currents going in different directions, and can we hit it and steer it? So that's what we call navigation. So part of this process is also an analysis to say, is there enough shear layers in the ocean where we're going to park? We can actually have some chance of steering. And then the other requirement was you had to be able to do this at multiple sites. You had to do this either all the time of the year or a permanent site, or we also want places where you can go maybe for 6 months of the year. The minimum was we want at least 3 sites. So I take no credit for all this. Niels is the wizard here on this. This is our web portal. So there's a landing page. Well, that's not working, is it? Need to get out of it. No. So this is our web page, and you can just type into Google HyperNav. Should be the first thing on there. So it just tells you a little bit about the program. We just kind of went over it, why we're doing all this, who the team members are. We created a dashboard, so it's a site we go to every day to just to say what's going on out there. So it tells you the campaign, where we are, where this float is right now, its current position, how old the data is over the last time to surface. So this one came out of the water 10 days ago. And so right now we don't have one in the water. This is why I'm leaving today, unfortunately, because I have to go back to go to Hawaii to put one in the water. So it also tells you, it gives you a graphical view of where we are. So this is the one that is off Maria that came out of the water because a wise fisherman saw something very weird floating in the water and hauled it in to shore. So this is sort of the track. We got it tracked from the distant from the shore, and then here's plotting the track over time. Yeah.
So my understanding of this is that you have very specific places that you want to deploy
Yes.
these sensors. So does that create an issue when you're calibrating the satellites? Because
just like if you were training a model, you're training or you're calibrating off the same space every single time. Would that create an issue?
If by having more sites,
By having few sites, so because you're not
Yes.
using the entire ocean.
yes,
Calibrate on.
that there was a couple, and Kelsey was, I think, involved in one of them. But I mean, yeah, the main one is that you could see some historical trends in some of the data products that wasn't always necessarily tied to the actual in situ measurement. It was tied to more, we think, more of a big problem in terms of the atmosphere corrections. It could be a lot, or there was some dependence on the location with the data. So this is why we want to do it, and they wanted it in multiple different sites so that we can get a better look, have a fleet of these things across the oceans to be able to say, okay, now if we took all these together, how much of it is due to latitude, longitude, all that, or does it just look great everywhere? So a good question. So you can also go on here, we collect all the overpass times at this current site or where it's going to be today. So we know when the overpass times are, so we can adjust. Because they do vary, so we can adjust if we need to in terms of when it's popping up. Since we have to run this thing for 60 days and there could be 4 or 5 of them in the ocean at the same time, we needed a dash and operations page. So this is the Maria one. It became critical, like I said, because you can see the fisherman hooked it, pulled it up on board and pulled it out. But it gives us some float health parameters, nothing really exciting here other than just how's the battery doing? How do we look in terms of observations? Are we getting enough? It gives us quick looks at the data. Oops. From the last observations, because we only come up once a day. So here's, in this case, we're parking at 500 each of these dots. That's where we sample. You can see when we get up to the surface, we really start sampling heavily. So most of our samples come within the first 20 meters of the water column. What's really cool here too is if we have all these locations, and this is one deployment we did. You can start to see, well, I'm steering it pretty well. It's kind of hanging around. This is all the locations over this period. But sometimes things don't look great.
Assuming everything goes according to plan, how long do you leave the profile? How long do you leave it in the water?
It's about 60 days before we run out of batteries, you know. It can go a little longer, but we have to shut off the hypernet so we're not transmitting so much data.
Like, you swap it out with the replica?
We have 7 of these. We're building 2 more right now, so we'll have 9 of them. So we're just constantly replace the batteries in the float, get a new hypernav, bring the hypernav back, get it calibrated.
Are these floats, like, is the data also going to the BDC Argo database?
Not at this point, not yet. No, we've had people interested, but right now it's delivered. We push it out to NASA as soon as we're done processing it, and it's posted on the web. So this is a bad one. Here's where we are, our dock site, the boat we use, and typically we've got ones trying to keep it, and then all of a sudden, we got lucky, actually. Alexander, through his contact network, with the boat operator we use, says, no way in hell I'm going out my 24-foot boat to get that. So luckily, we called around and Alexander found a deep sea fisherman. It's like, oh yeah, where is it? I'm gonna be there like in 3 days, man. So he went out and got it, luckily. Yeah.
So this is really cool, but now I'm trying to relate this back to the vicarious calibration.
We're getting there.
Okay.
I just want to give you eye candy and give credit where credit's due to Beals. But the cool thing was to drive it home. This is probably what you really want. there's the LW spectrum. So this is LW. We transmitted it through the air seeds. Here's the spectrum that NASA wants, and that's what we're pushing. Anybody can go to the site and download any data from any of our site and any of our campaigns. Just hit the download button, you'll get the full spectrum. All right, so now, good point. Let's drive it back home. All right, so we have 4 sites. We said west of the island of Hawaii, saw that one, south of the island of Puerto Rico, east of Moran, north of Crete. These all sites passed all those criteria I just went over. We did all this modeling, we did all the analysis historical. These were 4 of the best sites that met almost all the criteria and were affordable to get to and in and out of. Didn't cost us an arm and a leg. All right, where are we? I think I'm gonna skip over some comparisons, but we did a really quick field campaign to go compare against HyperNav and Mobi on one week. So that's what this is. This is Mobi, the dash line, and then the solid green is our HyperNav, and this is the difference between the two. It's not too bad. They're sort of within 2% of each other. All right. So you do all these, going through all these characterizations again, calibration, trying to just account for all the uncertainties, because like I said, NASA says I want less than 4% uncertainty in the blue through the green. You do all the instrument characterizations, thermal response, how sensitive you are to polarized light, all these things. You got to do all the characterizations, and you got to add in all this field effects, like how much uncertainty is there in self-shading, tilt, biofouling, wave focusing effects, all these things we can. So luckily, HyperNav right now is below 4% uncertainty. Okay, so again, we went to that first plot of gains. Remember, I showed you that took 40 to 60 of those observations. So this is using about 90 points from our 4 different sites, plus that new Maronet, plus the old Mobi one that I'll click. So remember that. What did I say? It takes about 2 years to get 40 just with Mobi alone. So here we are in the first year, we've doubled that. Okay, so these are all the different plots. They're all pretty close. All pretty close. Here's that oxygen. So not bad. We're still within 2.5% uncertainty on all these measurements, which is good. And then Mobi OCI and the NASA team started outputting data pretty quickly after launch, but they were starting to do the solar lunar cals, but they hadn't done these SVC calibrations. So this was the original sort of root mean square error of all the sources of air. This is a plot from Jeremy. This is sort of the baseline requirements. These are threshold requirements. So we're starting to be out of range in the blue spectrum. Once they added in our SVC measurements, now we got a lot better. Blue line. So now we're all on spec again. So depending on if they don't drift anymore or do anything more, we're getting pretty close to saying we're all good. No. That's it. Thank you. Oh, sorry.
So like the actual matchup, we have this, bucket-sized point source of radiometry data, and you're pairing that to the 9, or like how are you pairing that to the satellite data collection?
Oh, so we have the 2 arms. Are you asking how do we do that?
Or it's like,
Which one do we use?
yeah, it's like you have in situ data and you have satellite data.
Oh,
How do you connect them?
we take that in situ data from the HyperNav, like I said, and we have to pick either an average or a mean, depends on, that's why we do all these 2 of them, so we can get a relative measurement. We get it back, we calibrate it, we make a decision on which one's best to use, and we need to update it, we'll update it. But that measurement, you take that measurement, you run it through an atmospheric transmission model. It's based on the best properties we know at that point in time. It's going to be the same model of atmospheric correction that the satellite's doing to derive LW. So it becomes the top of the atmosphere radiance, which is exactly what the satellites measure. That's what we're comparing. That's what the gain is, the ratio between what's measured in situ and what's actually measured at the satellite at that same point in time. Does that answer your question?
Yeah, so I guess the follow-up is that you've got two knowns and you have this big atmospheric unknown. So are you sending any type of, are you getting any type of atmospheric measurements?
Oh, yeah.
Coincident at the same locations?
Yeah, that's part of, where they showed the spec one, the HARP, those are all on the PACE mission. They're using other atmospheric orbital perimeters and stuff, so they're trying to optimize the atmosphere correction based on other utility data, but there's still always some error in that process. And we're finding, because even like our Crete site, which gets occasional little spurts of Saharan dust coming up that way, you can start to see the data and the comparison pretty well, that the atmosphere correction isn't doing very well. All right, that's it.